Thank you for joining us today for a discussion of our research project, Predicting Air Quality Index using machine learning and deep learning models. This research was completed by a team consisting of Jinyuan He, Andrea Thomas, and myself, Joseph Edwards. To impress on you all why predicting air quality is such an important and timely research goal, and why it's something that deserves to be taken very seriously, I'm going to give you a global example as well as a local one. The global example on the left is from the Punjab region of Pakistan. Some organizations claimed that it was the worst air quality ever recorded in the world as of 2024. Up to 900 people were hospitalized due to this pollution event. Schools were closed, people were told to stay indoors, etc. The local example for me, at least where I live in Los Angeles, was the Palisades fire last year, which caused pollution levels in the air to spike, including dangerous heavy metals like lead, in one of the most densely populated regions in the country. 126 of the 138 WHO countries exceed their own PM 2.5 limits. Air quality index, or AQI as we'll call it, spikes have been linked to irreversible lung damage in children, premature deaths generally. People can't work outdoors in these conditions. It presents a very real economic problem with a very real cost to society. So what can we do about it? Well, if we can predict these AQI values ahead of time, we can help public health officials mitigate some of the worst consequences of the spikes. Vulnerable populations like the sick and elderly can be given time to prepare. Targeted interventions could be made, for example, stopping intentional burning or emissions producing manufacturing sites. Emergency responses can be prepared for ahead of time. Population behavior can be influenced. And so predicting these AQI values with machine learning and deep learning methods is the experiment we undertook. Specifically, we started with a linear regression to establish a baseline for model performance. Then we looked at different tree-based methods as well as deep learning methods.
Hi everyone, this is Jing Yuan. For this final project, I was mainly responsible for data cleaning, feature engineering, and building the baseline models. So today I'm going to walk you through how we process the raw data and how we reach our baseline model in size. We used a dataset from Kaggle, and the original file was pretty large, over 800 megabytes, covering more than 90 monitoring stations across Taiwan over 8 years. Our one major issue we have found is the real-world sensor fail pretty often. Some stations were missing time steps, some have long gaps, and others have inconstant records. Since our model is a time series forecasting model, we must ensure the data is continuous hour by hours. So after reviewing past research, we decide not to delete rows because that would break the time sequence. Instead, we use interpolation to rebuild missing values. Technically, we fill gap using the last valid observation and carry it forward. You can see the effect on the right-hand side of the slide. These missing values are replaced using the most recent valid measurements. Some stations have extremely sparse data and they would not reliable, and we remove them before running this interpolation. After all cleaning and rebuilding, our final data set contains 74 stations and about 23 million rows. Before perform the engineering features, we look at how the pollutants behave over times. Autocorrelation analysis show very clear seasonalities. AQI is usually better in summer and become worse in winter. So this pattern also repeats every year. I checked the ACF and PACF plus and pollutants like PM2.5, PM10, NO2, and NO6 also very clear slow decay. This means today's pollutant level is highly related to recent past value, which strongly suggests that we should include log features. We also use ECDF to compare normal and abnormal AQI days. We found that the pollutants such as PM2.5, PM10, NO2, and NOx shift to the right during the abnormal periods, meaning they come to be much higher when AQI is classified as bad. To catch this time series behavior, we create three major groups of features. Log features. Pollutants have a strong 24-hour autocorrelation, so we add 24-hour and 48-hour logs for major pollutants. This can help us to help the model to understand the daily cycles. And second, seasonal features. Since AQI pattern repeats yearly, just I mentioned before, winter worse and summer better. So we use sine and cosine encoding to represent the months. This avoids the artificial gap between December and January. And we use the lowering windows. We compute 8-hour and 24-hour lowering means and lowering standard deviations. This captures short-term accumulation and certain uh, fluctuations, which are important signal for AQI changes. For the baseline model, we use the linear regression. It's simple, fast, and good at capturing linear relationships. For one-step prediction, the model performed surprisingly well. We got an R-squared score of 0.93, which means the short-term AQI is highly predictable using recent pollutant level and loading features. However, the performance dropped quickly when we moved to 6-step and 24-step prediction. This suggests that as we look further into the future, AQI become more non-linear and harder for a linear model to capture. So this result is expect linear regression struggle with a complex temporal pattern and long-term dependency. So next step, our teammates, uh, Joseph and Andrew would introduce how to use a tree-based model and deep learning to solve this kind of problems.
Next, we'll look at tree-based methods for predicting AQI, which offer a research-supported technique for better capturing nonlinear relationships and complex feature interactions. Specifically, we tried two different methods, the random forest and XGBoost. Random forest and XGBoost are both ensemble methods that combine multiple decision trees, but they differ specifically in how they build and combine those trees. Random forest uses something called bagging or bootstrap aggregating, where many independent decision trees are trained in parallel on random subsets of the data and features, and then their predictions are averaged to reduce overfitting and variance. XGBoost, which uses extreme gradient boosting, where trees are built sequentially, with each new tree specifically designed to correct the errors made by the previous trees. We attempted to predict AQI for different time windows into the future, 1 hour, 6 hours, and 24. The true air quality value is the black line that you're seeing here. I chose this slide to highlight a problem that we faced with our tree-based method prediction, as well as a problem that happens for many time series prediction problems, which is that the farther you try to predict these values into the future, the more unreliable those predictions become. So as you can see, the black line, which is the true values, are pretty closely linked to the 1 hour into the future prediction. And the larger the time window becomes, the more off the true value those predictions become. Of the two tree-based methods, both had errors that were reduced up to 50% compared to the linear regression baseline. However, XGBoost slightly outperformed the random forest method. As you can see here with this graph, XGBoost has the slightly higher R-squared value and has a slightly lower MAE and RMSE error value compared to the random forest. We also took an experiment to answer the question, how do these tree-based models compare if you take into account the global set of all air measurements, or if they were localized to a specific station? And so we selected a random station to train a tree specifically on the values from that station and compared it to the baseline model, which uses these tree-based methods to predict using a collection of every air quality station. And what we found is that they performed pretty closely, but overall, the global model did outperform the local one. This was likely due to the ability of the global trees to better capture more generalized trends across all the stations.
Great, so in this section, I'm going to dive deeper into our deep learning approach to predicting AQI. While our linear and tree-based models performed reasonably well at shorter horizons, they struggled with the complexity of the data when we took the time horizon past 6 hours, as Joseph and Jinyuan just covered. Deep learning models are specifically designed to capture the nonlinear interactions that simple models often miss, and that's what we wanted to pursue here. We implemented two specific architectures to tackle this. The first is feed-forward neural networks, and the second is long short-term memory networks. Our goal here was to move beyond simple trend prediction and actually model the complex shape of diurnal AQI changes. In the FNN architecture, information flows strictly from input to output. We use this to compress our input data, which included lag features and rolling windows, into higher-level abstract features. However, FNN doesn't inherently understand time, and we had to rely on our feature engineering to translate this into a static concept for the model. Because of the time dependency issue, we also decided to use an LSTM model. And unlike the FNN, the LSTM utilizes an input, forget, and output method. This allows the model to regulate information flow, which can better capture longer-term trends. Moving into our hyperparameters, like all deep learning model construction, we use these to control the training process itself. Ultimately, we needed to have proper tuning to ensure our model was complex enough to learn the patterns of the data, but was also constrained enough to avoid simply memorizing the data, which would end up overfitting. There were 4 key hyperparameters I want to quickly touch on. So first, we use the rectified linear unit activation function for all the hidden layers. This activation function accelerates convergence via SGD and mitigates the vanishing gradient problem. Traditionally, as a network gets deeper, the signals telling the model how to learn, which are also known as the gradients, get smaller and smaller until they vanish and the model stops learning. With ReLU, it doesn't squeeze positive inputs into a tiny range and instead passes them through, which keeps the gradient strong. Next, we selected Atom as an optimizer, and this proved to be very useful because it uses adaptive learning rates, which are particularly effective for the noisy environmental sensor data that we were working with. For loss function, we optimized for mean squared error, because in air quality, a massive spike in pollution is dangerous, and we wanted to connect our model back to the business problem at hand. MSC penalizes large errors more severely than small ones, so it allowed us to prioritize the detection of these dangerous spikes. Finally, to prevent overfitting, we applied a dropout rate of 0.4, which was 40% of our data. This forced the model not to rely on any single feature. Initially, we had actually started out with a dropout of 20%, but we found that the model was overfitting, so 40% ended up being a better fit for this data. When we ran these 2 models, we found that LSTM proved to be the stronger performer. On this slide, we're looking at the training and validation loss charts for our 2 models, which plot the model's error on the y-axis against the number of training epochs on the x-axis to diagnose how well the model is learning. The training loss indicates how accurately the model fits the data it's already seen, while the validation loss measures its ability to generalize the new unseen data. On the left, you see the FNN performance. Notice the gap between the blue line, which is training, and the orange line, which is validation. This divergence indicates overfitting because the model memorized the training data, but it failed to generalize the new data. The orange validation line is also a little bumpy, which suggests the model is unstable on this unseen data. Now, if we take a look at the LSTM performance on the right, this is what we want to see. The validation loss drops rapidly and tracks closely with the training loss, and it stabilizes around epoch 3. This stability indicates that the LSTM successfully learned the sequential dependencies of the data without overfitting. You can also see the model stops after epoch 8 because we used early stopping. We did use a value of 5 here, but we probably could have used an even lower number and saved additional resources, so it stopped earlier. Finally, looking at our output metrics on the right, we can see just how effective our LSTM model is at predicting AQI. We end up with an R-squared of 0.99 and an MAE and RSME that is a fraction of the FNN models. This is a good indication that LSTM is a better fit for this type of problem than FNN. Finally, we want to compare how all 3 of these algorithmic families perform against each other. Just to recap from Jinyuan and Joseph, we had 3 different approaches here. First, linear regression was simple and interpretable. It worked great for 1-hour forecast, but failed significantly at longer horizons because it couldn't capture nonlinear dynamics. Next, our tree-based model captured general trends, but it exhibited trend smoothing, especially as we moved the forecast horizon out. It often missed the amplitude of rapid short-term fluctuations and couldn't be relied on for longer-term forecasts. Finally, as I just mentioned, deep learning provided us with a high-fidelity forecast via the LSTM model. It was the only method capable of modeling the specific shape of diurnal changes with high precision and some really nice performance metrics. We can see this clearly in these 24-hour forecast plots. On the top, we have linear regression. You can see the orange prediction line detaching from the blue true prediction as time goes on. It's essentially failing to capture the complexity of the data here. On the top right, we have one of our tree ensemble methods, XGBoost. It captures the rhythm, but it smooths out the peaks and valleys. Just one note on this chart as well, the true AQI line follows a different trend in this chart than the other 2 charts, and this is attributed to the difference in sampling and batching techniques in the XGBoost model. There are more details in the full paper, but just to summarize, we made our trees aware of which weather station the data was coming from and used a stratified sampling across those stations. So this variance is by intention, and just wanted to call that out. Moving on to the bottom, this is where we have our LSTM model. The orange line tracks to the blue line almost perfectly for all the reasons I talked about in the last section, and deep learning proves to be the best predictor here. It captures not just the direction of the trend, but also the complexities of the data. Finally, to tie everything together, while all of our models worked for immediate hourly forecasting, really only deep learning was able to capture the nonlinear nature of AQI dynamics over these longer horizons. As we've mentioned a few times in this presentation, this nonlinear nature and the longer-term forecasts are what make this critical to real-world applications. We need to make sure our model could actually be used for its intended purposes. The last thing I'll add is that we were able to address computational cost. We were working with a massive data set with some pretty complex trends. By optimizing the hyperparameters and using 32-bit precision, we were still able to make our best performing model also perform efficiently. If we were putting this out into a real-world application, we would want to have something that was reproducible and production ready, and that's what we've achieved. Thanks for watching. There are more details in the paper, and I'd encourage you to take a look.